Many natural phenomena follow the law that an amount A varies with time t according to the function a of t equals a sub naught e to the kt, where a sub naught, the value in front of e, is the initial amount. If k is greater than 0, then it is considered a growth equation, and if k is less than 0, it's considered a decay equation. So here the number n of bacteria present in a culture at time t in hours obeys the law of uninhibited growth. The formula that they give is n of t equals 1000 e raised to the 0.01 t. So what is the initial amount? So if you're not sure, the initial amount is when time equals 0. So you can just plug in 0 for t. So we can say that n of 0 equals 1000 e to the 0.01 times 0. And you can just plug it into your calculator. That's not too difficult to do. So 1000 second ln of 0.01 times 0. And we're going to get 1000. So 1000 bacteria. But if you remember what I said before, the number in front of E here is called the initial amount. And so it matches up, so you can do either one to prove that it's the initial amount. Now, what is the growth rate? The growth rate is K, and K is the number in front of T in the exponent. So it is 0.01. But we don't want 0.01, we want the percentage. So you just multiply 0.01 by 100, and we're going to get a growth rate of 1%. Now, what is the population of bacteria after 4 hours? Well, we know our t value is 4, so we can just plug in 4 for t. So we're going to get n of 4 equals 1000 e to the 0.01 times 4. And unlike the first one, we're not going to be able to just look at a number and see, so we're going to have to use our calculator. So 1000 second ln of 0.01 times 4. And we're going to get 1040. And again, we don't want to do like half of a living creature, even if it is bacteria. We're going to keep with the same rules. We're going to always round down to the nearest whole number. So we can say that there are 1040 bacteria. At least living bacteria. Next, when will the number of bacteria reach 1700? So we need to find the time, which means we need to know the amount. And 1700 happens to be the amount. So we're going to set our equation equal to 1700. So 1700 equals 1000 e to the 0.01 t. And now we're going to solve. We're going to divide 1000 over and simplify, and that's going to be 17 tenths equals e to the 0.01 t. Take the natural log of both sides and get ln of 17 tenths, put in parentheses for emphasis, equals 0.01 t, because ln e is just going to go away. And now I divide both sides by 0.01, and I'm going to end up with ln of 17 tenths divided by 0.01. That'll be my time, but I don't know what that is in time, so I'm going to have the calculator tell me what it is. So ln of 17 tenths divided by 0.01. And I'm going to get 53.1. So 53.1. And knowing what time is in, time being hours, we say that this takes 53.1 hours. for the bacteria to increase to 1700. Now, when will the number of bacteria triple? Well, we got to know our initial amount, which was in part A, which was 1,000. So triple that would be 3,000. So we're going to set our equation equal to 3,000. 0.01t. And now we're going to solve for t again. Divide both sides by 1,000. We're going to get 3 equals e to 0.01t. Natural log of both sides. ln 3 equals 0.01t. And again, ln e just goes away. Divide both sides by 0.01. So ln 3 divided by 0.01 is how long it'll take for it to triple. Which again, I want to know a number, not this weird looking thing. So I'm going to plug it in here. So I get ln 3 divided by 0.01. And I'm going to get 109.9. So 109.9. And our units of measure for time are in hours. So 109.9 hours for our bacteria to triple in size.